For decades, we organized our digital world into neat, orderly rows, but that structure is reaching a breaking point. As you can see, our systems are exploding outward, struggling to contain a flood of unstructured information, images, voice notes, and raw human conversation. Consider how this affects something as simple as shopping online. You might search for a warm zip-up jacket, but if the store's catalog only uses the phrase thermal fleece pullover, you get 0 results. This diagram shows the logic of a traditional relational database. It relies on exact matches. Because the string of letters in jacket doesn't match the letters in pullover, the system signals a total rejection. It cannot see the conceptual link between the two. When a system can only recognize literal characters, it loses the intent behind the query. We need a way to move past the spelling and get to the meaning. To fix this, we have to stop organizing data by alphabetical or numerical order. Instead, we have to organize it by what it represents. This creates a vector embedding. Machine learning models translate raw data, like a paragraph, into dense arrays of numbers. These numbers act as coordinates on a mathematical grid. Because cat and kitty share semantic traits, they're plotted together. Unrelated concepts, like banjo, land far away. By turning concepts into spatial coordinates, we found a way to use pure math as a proxy for human understanding. In a real-world system, this isn't a simple 2D graph. These models operate in hundreds or even thousands of dimensions at once, creating a vast, glowing star field of billions of individual data points. Navigating a space this complex requires a specialized kind of infrastructure. This is the vector database, a system built specifically to store and index these high-dimensional mathematical coordinates. This diagram shows the similarity search in action. When you submit a query, the database plots it in the grid and expands a search radius. It doesn't look for an exact match. It just identifies the data points that are physically closest to your query. Because checking every single point in a massive database would be too slow, these systems use approximation algorithms. They trade a small amount of absolute precision for the ability to find the nearest neighbors in milliseconds. By calculating this physical proximity, computers can finally retrieve information based on the context and the vibe of your search, rather than just the vocabulary you used. This isn't just theoretical math. It is the engine behind the personalized recommendations you see on streaming services every day. Your viewing history becomes a coordinate. The system doesn't check genre tags. It simply suggests movies mathematically closest to you. Banks use this to stop fraud. Normal spending forms a tight cluster. A transaction appearing far outside it is immediately flagged as a mathematical outlier. Complex human behaviors, from what we want to watch to how we spend money, can now be analyzed by calculating the simple distance between points in space. However, relying exclusively on meaning creates a new problem. Vector search is so good at finding similar things that it can sometimes struggle with specific hard facts. If you search for the species Alaskan pollock, a pure vector search might return high-quality results about fishing for salmon because the context is so similar. It understands the vibe of fishing, but it might miss the specific fish you actually named. Then there is the issue of metadata. As this diagram shows, spatial distance can't easily calculate a hard boundary like only show items under $50. You need a different kind of logic to handle those strict constraints. To be truly effective, an artificial intelligence needs both conceptual understanding and rigid, rule-based boundaries. This has led to the rise of hybrid search. These systems run a semantic vector search and a traditional keyword search at the exact same time. This diagram shows the results merging. By using fusion algorithms, the system combines the conceptual reach of vectors with the literal precision of keywords, ranking the best possible answer at the top. We can then layer on metadata filters to ensure the results aren't just similar, but also factually correct, checking for the right price, the right date, or security clearance. This setup allows an AI to instantly retrieve facts from a company's private documents or a user's past history, giving the model a source of truth it wasn't originally trained on. By grounding AI in these specific retrieved facts, vector databases serve as the essential memory layer, bridging the gap between human intent and computer retrieval.